Okay, so in today's lecture, we're going to talk about the theory behind something called logistic regression. Okay, and to motivate this problem or this algorithm, we're going to suppose that maybe we've been asked for whatever reason to look at students' GMAT and SAT scores and try to predict whether or not they will be accepted to some university. Okay, so we're trying to classify based off of two scores, right? So in order to do that, we're going to need historical data, right? We're going to need something to learn from, right? Like right now, I have no clue what like good GMAT and good SAT scores are. I never took either one of them, right? So like, I have no clue. So I'd have to ask, okay, where do I get this data? So suppose that you do get the data, right? So then we have maybe like a pandas data frame. So we have like student, okay, so we have like student 0, 1, 2, ... And then suppose we have like n of them, okay? And then for each student, we have a GMAT score. So I'll say maybe like G1 or G0, G1, G2, ... all the way through Gn. Okay, and then we'll have maybe we'll have SAT scores. So maybe S naught, S1, S2, ... through Sn. Okay, and for each of these scores, these are historical records, we can look at whether or not they were admitted or not, right? So this column, we can have a label corresponding to whether or not the student was admitted or not. So maybe this student here was not, so maybe label 0. Maybe the next student was, maybe the next student was, and maybe that last student was not. Okay, so this is a classification problem, right? We need to use this data to make predictions on outside data, right? So you would probably want to, and most definitely want to, maybe truncate this data somewhere and then train here and then test here. Okay. Assuming that the data is shuffled, right? You don't want all the ones to be down here and all the zeros to be up here. You want to shuffle the data. Okay. So this is a binary classification problem, similar to the perceptron, right? However, these labels in general will not be completely deterministic, right? There could be instances where same GMAT, same SAT score for two different students occurs where one is admitted and one is not, right? So we cannot use the perceptron to do this effectively, really. We can try, and I encourage you to, but what we really want is maybe to predict a probability and some type of measure of how likely that student is to being admitted given those scores, right? It might not always be correct, but we just want the best that we can do. Okay. So what does our data look like? Well, we have our feature vectors, which is GMAT, SAT, and then we have our labels, y, which are just elements of the set 0, 1. Okay, so that's what our data looks like. So let's formulate this in a similar manner that we did with the perceptron and we did with the recursion. Okay, let's formulate this as a simple, shallow neural network. Okay, so I'll say maybe like G goes in here, and then S goes in here. And then of course, we can't forget our bias, which goes in here, right? And with these shallow networks, we're going to feed that into a neuron. Where we'll have maybe a weight 1, weight 2, and a bias. Okay, and as I mentioned before, these neurons will have a pre-activation and a post-activation value. Now, different than last time, I'm going to now introduce new notation. The pre-activation will now be denoted by Z. Okay, so here, Z is equal to W transpose times X plus B. Okay. Now, with the sigmoid function, not the sigmoid, with the perceptron, the activation function was the step function, right? Here's the sign. With linear regression, it was just the linear output. Well, now we want to output something in the interval between 0 and 1. We want a probability. Okay. So the function that we're going to choose as our activation will be sigmoid. And sigmoid of a given input is simply 1 divided by 1 plus e to the power of minus the input. This function will look something like this. There's 0 is down here and 1 is up here. Okay. So now I'm going to have to introduce more notation. A is now the post activation. Okay. And this post activation is simply your activation function applied to your pre-activation. Okay. Now it's kind of silly to do it on this single neuron, but it's important that I introduce this notation now, because when we get to deep learning, deep neural networks, this is the standard notation that I'm going to adopt. Okay. All right, so now we're going to output y hat. Okay. Now, we won't need the A too much today. I'm just introducing it so that you have this in your notes. We're just going to think of y hat as sigmoid applied to Z. Okay, so that's our predicted probability. Now, if we choose random weights and biases, this model is going to spit out a number between 0 and 1, and we can already badly make predictions as to what the likelihood of being a 1 or a 0 is. But how do we choose that? How do we decide 1 or 0 given a probability? We're only spitting out like one number, but there's two choices, 0 or 1. It's binary choices, right? So let's make a few observations that we need to make. So one each example xy belongs to class 0 or class 1. Okay, that's kind of obvious, right? Each of those pairs, right? Next, we need to, well, before I say that, these are complementary to each other. You're either that or that, right? But now we need to assume that, not assume, we can maybe assume this. Each example, or maybe not each example. The examples are pairwise independent. And what do I mean by that? Well, I mean that we're assuming that these, like this person's admittance did not determine this person's admittance. We're assuming that. It might not be the case, maybe, but that's what we're going to assume. Okay. And these two things together imply what is called IID. Independent and identically distributed. So that distributed part also, I need to explain that. That doesn't appear here, and I should have. We're assuming that the distribution of the zeros and ones is more or less the same. They follow the same distribution. We're not seeing, at least in our training data, right? Because, for example, if the majority are all ones and there's like maybe 2 zeros, this might throw off out of sample predictions. And we want to gather good training data where the data set is more or less, the features are independent of each other and follow the same distribution. Okay. So that's what we're going to assume. And in your notes, you should definitely write that. We're assuming that the examples are generated under the same distribution. This is not always the case, and this is where data preprocessing and looking at statistical measures of the data is important. Okay. So what do we want? And so let me start back over here. What do we want? Well, just consider the following formula. The probability of y given x. We're just going to go ahead and decide this can be y hat if y is equal to 1, and 1 minus y hat if y is equal to 0. So what we're doing when we're writing this equation here, this is conditional probability. So given the input x, probability y, right? Y given x, right? And we just decide that y hat is going to denote when y is equal to 1. The complement, this is a probability, right? Y hat is interpreted as a probability. So not y hat is 1 minus the probability, right? Which is the other label. So we're assuming that our target y hat should look like that, is associated with y equal to 1. So what do we want? We want high y hat when y is equal to 1. And low y hat when y is equal to 0. Right? So this probability, like, of getting the correct output, right? Given that input. So if y hat is high when this is the case, right? It's good. When this is the case, y hat is low, probability is closer to 1. Right? So we want to maximize y hat when that, and then maximize this quantity when that. So maybe I'll just write that out. So maximize y hat when y is equal to 1, and maximize 1 minus y hat when y is equal to 0. Okay, so let's go back to what we're doing. We're spitting out we're feeding forward into this single neuron, GMAT, SAT scores, and a bias here, right? We're spitting out a probability. And we want this to be high when the label is equal to 1, and we want this to be high when the label is equal to 0. And we want to somehow train these weights to do that for us, right? So how do we train the weights? We need a loss function, right? The only way to train the weights is with a loss function. That way we know when we're doing bad, right? So we need to somehow come up with an appropriate loss function that's going to maximize this. Maximize this, right? Okay. So we can do this. And we're going to derive exactly how to do this. Okay. In particular, we can write this conditional probability in a very nice way by recalling Bernoulli. And I always misspell his name for some reason. I think it's that U there. So if you recall from maybe your prob and stat courses, there is this notion of if you have two outcomes, right, like flipping a coin, there's this nice closed formula for that. It looks something like this. So the probability of y given x, we can write as y hat to the power y times 1 minus y hat to the power 1 minus y. So why would this formula make sense for us? Like, yes, if you look through your problem stat notes, you'll see it, but why does it make sense for us? Well, what happens when y is equal to 1? Well, the probability of y given x under this formula is going to be y hat to the power 1 times 1 minus y hat to the power 0, which just leaves us with y hat. Good. Okay. So what about when y is equal to 0? Well, probability of y given x is now going to be y hat to the power 0 times 1 minus y hat to the power 1, which is just equal to 1 minus y hat. Okay, so this notion here now looks like this. We have y hat when y is equal to 1, 1 minus y hat when y is equal to 0. So what do we want? We want to maximize this. Okay. So that's what we're going to do. Right? This is what we want. We want the correct probability for that label given that input. So maximize that. Everything's going to work out. We just have to maximize that. But first, we need to do a little bit of algebra to get there. And it's kind of messy. In particular, we're going to take logs and do all kinds of things with them. So I'm going to take the log of both sides of that equation right there. So log of the probability of y given x is equal to the log of y hat to the power y times 1 minus y hat to the power 1 minus y. And now we can use properties of logarithms to expand this. And then we know that the exponents become coefficients, or they can. Like that. All right, so we have this funny looking log thing here now. And we know we want to maximize this. So recall that the log function looks like this, right? Just some increasing function, right? So because of that, maximizing this probability is the same thing as maximizing this log probability. Okay? So we want to maximize this, which is equivalent to maximizing this. Now, we don't know how to deal with that. Well, we sort of do, but we prefer to minimize things, right? So we want to minimize negative of this. Okay. And this is the same thing as saying minimize minus y log y hat minus 1 minus y times log of 1 minus y hat. Okay. So this, minimizing this is going to maximize that, which is what we wanted. We want to maximize this probability, right? We want to maximize what happened, that, right? So if this is what we're minimizing, what are we typically minimizing when we use the previous techniques from the previous lectures? We're minimizing the loss function. Oh, this is a good candidate for our loss function. So this is what our loss is going to be. Okay, and this loss function has a name. This is called the cross entropy loss. And to be a little bit more specific, technically the binary cross entropy loss, but this is the general form that you'll see. Okay. So for a given single input, think about it. We feed into the neural network, the neural net, the single neuron. We feed in an X, we get out a Y hat, and then this is our loss for that Y hat. See it like appearing all over the place? Okay. We know how to minimize things, right? And the sigmoid function is differentiable, just an exponential, right? So we can find the gradient with respect to the weights and biases now. And that's what we're going to do. Okay. Before doing that, though, I need to make note of a few things. And that is that, so the derivative of the sigmoid has a nice closed form. Like that. Now, if you took Cal 1 with me, or the Math 2421, this is like one of the assignments I have for my students to derive this and show that this is true. I don't have time to do it in today's lecture, but I encourage you to verify this. Okay. And then also, what else? I wrote down a few things to recall. Oh, this, because I'm sure you forgot this. So ddx of log of f of x is equal to 1 over f of x times 1 over the natural log of the base. Here the base is 10 times df dx. Right, so f is a function of x, so using the chain rule, this is just calculus 1 material, both of these things. Okay, and then what else? Oh, you have to just remember that y hat is equal to the sigmoid applied to z. But what is z? Z is that linear combination. So if you want, in your notes, maybe you can write W1 times X1 plus W2 times X2 plus your bias. It might help when we're deriving the gradient. Okay. So this is just like previous information from, well, those 2 points are calculus 1, and this is just what we're using. And now our loss in terms of W and B with respect to a given X there is just negative Y log Y hat minus 1 minus Y times log of 1 minus Y hat. And this is what we need to take the derivative of with respect to W's and B's. Okay, so let's go ahead and do that. All right, so when doing these tedious derivations of the partial derivatives of loss functions, especially when you have a lot of variables, it helps just to focus on one at a time, right? We know that W has 2 things in it, right? And there's only one B. So let's find the partial derivative with respect to W1. If we can do that, then W2 is just as easy. So we're going to focus on finding the partial with respect to W1. All right. right, so we're just going to apply this operator on both sides. That's y. Okay. I mean, it's simple enough. I haven't really done anything besides just apply it on both sides. Now, the y's are just the labels, right? They're not functions of W1 at all. The y hats are the functions, right? So when I distribute in this operator, I can kind of just take out those y's in front, or the coefficients. Like that. Okay. Now, it might help to remember now what y hat is. Y hat is just the sigmoid function applied to pre-activation Z. So I'm going to run out of room, but I should probably write that just so you see it. Okay, almost there. Okay, so why did I do that? Well, look, we have the derivative of log of a function. That's why I wrote down this. We have the derivative of log of a function. Okay, so let's go ahead and figure out what this first piece is. What's that derivative right there? Okay, so I'm going to do it over here to save space. So partial with respect to W1 of log of sigmoid of Z, okay, is equal to, well, 1 over sigmoid of Z times 1 over natural log of 10 times the derivative of sigmoid of Z, right? With respect to W1. So, but now Z is a function of W1, right? So we have to apply the chain rule, the derivative of the outside times the derivative of the inside. So what do we get? So the derivative of the outside is just sigmoid prime, right? Which is this. Right, the derivative of the outside. So it's just going to be sigmoid of Z times 1 minus sigmoid of Z times the derivative of the inside, Z, right? What's the derivative of Z with respect to W1? There's Z. The derivative of Z with respect to W1 is X1. oh, look, that divides out, right? And what are we left with? 1 over natural log of 10 times 1 minus sigmoid of z. What's sigmoid of z? It's really just y hat, right? Like that. So that's what this becomes. So we get negative y times 1 over natural log of 10 times 1 minus y hat times x1 minus this other stuff. Oh, we got to do the same thing for that. We have to figure out what that derivative is. Well, shouldn't be too bad. Let's do it. Okay, well, this is going to be equal to 1 over 1 minus sigmoid of z times 1 over natural log of 10 times the derivative of the inside, right? Derivative of the outside is this business times the derivative of the inside. So when we take the derivative of the inside, that 1 just goes to 0, right? And we're just left with negative, right? Negative times the derivative of that. So negative the derivative of this. And we did that before, right? It's just this nice closed form. Times the derivative of z, the inside, which is what? With respect to W1, it's just X1. Oh, that and that divide out, right? So we just get that this is equal to negative 1 over natural log of 10 times sigmoid of z times X1. But sigmoid of z is just y hat. Or not, yeah, it's just y hat. So that's what this piece becomes. Oh, there's a negative right there, right? That negative here times that negative there is going to make it a positive. Good. Now, when performing gradient descent and looking at the partials, it doesn't matter that there's constants right here. Like these constants don't change how gradient descent is going to go down, right? So what we're going to do, just for notational simplicity, is we're just going to drop those constants out because we're not going to have to worry about them, right? Just like minimizing the parabola x squared is the same thing as minimizing the parabola of 2 times x squared, right? It's the same type of idea. So it's a mess. We don't need those logs appearing everywhere. So we're just going to drop them. It's whatever, have them go away. So then I'm going to factor out that x1 after I drop those natural logs out, just because we don't care. And then what do I have on the inside? I have minus y times 1 minus y hat plus y hat times 1 minus y. Okay, so now just need to do some more algebra. So what does this become? I should have used brackets here to be clear about what's what. Right, so if I distribute in, I get minus y plus y times y hat plus y something's off, and you're about to see why. Oh, no, this is y hat, I'm sorry. Minus y times y hat. Right? That times that, that times that, 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 and that's what that. Oh, look. Those go to 0. So what do we get? We really get just positive y hat and a negative y, all times x1. There's your partial with respect to W1. Look at that. Doesn't that look exactly like the partial that we would have found for linear regression? It does. It's just the difference of the outputs, right? The output in the label times your x1. Okay. So all of this business that we just did basically is telling us that partial L, partial W I is equal to our prediction minus our output times X I. If we did the same thing for the partial with respect to W2, it'd just be a 2 right there. The coefficient of W2 is X2. What about when we do the partial with respect to B? The partial with respect to B, there's no coefficient of B, right? So it's just going to be a 1 out there. So then we can just say that the partial with respect to B is just equal to y hat minus y. Right? When we derived all this stuff, and suppose we were taking the partial with respect to B, everything would be the same except for when we took the derivative of z. The derivative of z with respect to b is just 1, right? So that's why I'm writing that. All right, those are the partial derivatives. So now, we have everything in place. So notice now, though, that we're computing the loss with respect to one entry, one feed forward, right? And because of that, when we derived these partials, we're not finding the full gradient of the loss. Because the loss, really, we should take the loss over the entire data set, right? And that's precisely what you would do to measure your loss. But to update your weights and biases, all you really need to do is perform stochastic gradient descent, one at a time. So your full loss is going to be equal to your sum of your losses for your weights, bias, given X. So over all training instances X, or test instances, right? And for stochastic gradient descent, So what would the pseudocode look like for this? So one, pick your learning rate, alpha, okay, and then two, so you could say there's a few different ways that you can do this. You can perform updates to your weights and biases until this loss stops moving. Right? And at some point, the loss is going to kind of bottom out. And you can decide that's when you want to stop. Okay? But for our purposes, let's just like do it a certain amount of times. Right? So or maybe I equals 1 to max iterations. Do randomly pick X from training data. And then feed forward X into the neural network. Which will give you your y hat when you do that. And then 5, W becomes W minus your learning rate times y hat minus y. Oh, I should say pick x, y, not just x, pick x, y from your training data. Times x. Now these are vectors now. You just like stack your partials in a vector. And then do the same thing for your bias. Like so. And then after you've done that, your weights and biases have been updated. Okay. So again, when I say feed forward, I mean really that we're feed forwarding into our small neural net, and it outputs this y hat. Okay. So that's it. That's logistic regression as a simple 1 unit neural network. Okay. So now, I don't know if I have it on my computer, but it wouldn't be too hard to program this right now. But maybe that'll be it for today's class. And I just email you a Jupyter notebook to play around with this idea. And there's a data set of GMAT and SAT scores that I'm going to send you. And maybe try to program it on your own first. It really is just this. Okay. But then look at the notebook that I'll send out, and if yours isn't working. Okay. Now, the notebook that I sent out does it more or less like this, sort of. But that's not really the best way to do this because we're repeating ourselves, right? Like, think about it. With the perceptron, with linear regression, with this, we are repeating ourselves over and over again. We're writing the same code, right? What we need to do, and what I'll do for you and give you an example of, is to build our own object or make our own object, our own class. Maybe call it maybe single neuron is the class, right? And so for like, what are the components, right? Well, maybe that's a little too big. Well, so what do we need to make our own class for a single neuron? Right, what do we need? We need the number of inputs, right? So like this right here would tell us, well, we need to know number of features maybe. Right? When we instantiate our object. We'd also want to know, should we use a bias? It might be interesting to compare performance by removing the bias sometimes. Okay. And what about this thing? Well, this function we can choose, right? If this is like that, just the linear function, then we have linear regression. If it's the sine function, we have the perceptron. If it's the sigmoid function, we have logistic regression, binary logistic regression. So then, if we instantiate with a number of features and a bias, we could also tell it what its activation function is. So we need an activation function. Right? And along with that, we need also a loss function. Which in turn means that we need the gradient as well. Approximate gradient, right? So if you instantiate an object like this, you make your own object and then instantiate it, then you can choose when you make it whether or not it's that, or that. And you have it to use over and over again, opposed to writing this every time, right? So I'll do that for you, but I encourage you to try it on your own. Okay, after you at least get this working on the data set that I sent you. All right, so that'll be it for today's class.